Welcome to this explainer. Today, we're taking what might look like a dry list of 7th grade math standards, and we're totally transforming it. We're going to build the ultimate toolkit for understanding our actual reality. You know, if you've ever stared at a math textbook and thought, come on, when am I actually going to use this stuff in real life? Well, you are exactly in the right place. We're diving right in to decode the mathematics of how we measure, scale, and literally predict the world around us.
So how do we mathematically compare the world around us? I mean, that is the fundamental question here. Math isn't just sitting in a room counting isolated objects in a total vacuum. No, it's a highly evolved language designed specifically to compare different quantities. Think about it. Whether we're checking the price of groceries, looking at the speed of a car, or even checking the probability of rain for the weekend, we are inherently comparing one thing to another.
Okay, here's our roadmap for today. We'll start with ratios and proportional relationships, then look at the power of percentages, before moving into math in the real world. After that, we'll cover geometry and scale drawings, and finally, wrap things up with probability and random sampling.
All right, Section 1, Ratios and Proportional Relationships.
Imagine you're just standing in a store. How can we actually decide if two quantities are proportional? Well, it's like calculating the total cost based on a constant price per item. If your total cost, let's just call that T, is always proportional to the number of items you're buying, which we'll call N, at a constant price of P, we can express that relationship perfectly as an equation. It's just T equals P times N. And if you plot these numbers in a table or graph them on a coordinate plane, you can visually see if the relationship forms a straight line going right through the origin. That straight line? That is your ultimate visual proof of proportionality.
Now, the really crucial point here is wrapping our heads around this specific vocabulary term, because the constant of proportionality is exactly what lets us compute complex fractional rates. You know, things like walking miles per hour. Let's say a person walks a half mile every quarter hour. How fast are they actually going? Well, by finding the unit rate, or that constant of proportionality, we calculate the complex fraction of 1/2 divided by 1/4, and that reveals an equivalent rate of exactly 2 miles per hour. Understanding this one single concept totally unlocks our ability to read tables, graphs, and diagrams with absolute clarity.
Moving right along to Section 2, the power of percentages.
You know, our human brains actually miscalculate percentages and odds all the time. It's totally natural, but converting a decimal into a percentage is incredibly logical when you break it down into a foolproof 3-step mechanical process. First up, you take a decimal, let's say 0.65, and write it as a fraction over its place value. So that's 65 over 100. Step 2, you just multiply that fraction by 100. And finally, step 3, you literally just insert the percentage symbol at the end. Bam! Just like that, a decimal transforms into 65%. It's a brilliant little mechanical process for shifting between different mathematical dialects.
Now, look at these two identical mathematical concepts side by side. Seeing that adding a 5% increase is the exact same operation as multiplying by 1.05, I mean, that truly sheds light on how algebraic expressions work in the real world. On the left, taking a value a and adding 0.05 times a makes total logical sense for a 5% increase, right? But rewriting it into the single expression on the right, 1.05a, shows us this incredibly powerful shortcut. Rewriting expressions in different forms doesn't just change how the math looks on paper. It completely shifts how we understand the relationship between the quantities. It's a real game changer.
Okay, Section 3, Math in the Real World.
Take the number $27.50. Let's say a woman making $25 an hour gets a 10% raise. She just adds 1/10 of her salary, which is $2.50, to achieve this new hourly wage. Understanding rational numbers and percentages isn't just some boring academic exercise. This is about navigating your actual livelihood. By applying the properties of operations, we can confidently calculate that 10% of 25 is $2.50 and quickly arrive at her new salary of $27.50. Let's say you're doing a little home improvement over the weekend. You've got a towel bar that is 9 3/4 inches long and a door that's 27.5 inches wide. Now, instead of immediately panicking over the messy, complex fractions, you can just use mental math to quickly check if your exact computation makes sense. So, round the door up to 28 inches and round the bar to 10 inches. 28 minus 10 is 18. Divide that by 2, and you get 9 inches of space on each side. This rapid mental estimation is such a powerful strategy to ensure your exact arithmetic is actually in the right ballpark.
Mastering these multi-step ratio and percent standards absolutely empowers you to navigate the financial realities of our world with total confidence.
Whether you're calculating simple interest on a loan, factoring in sales tax at the register, computing markups in retail, or determining the tip for a server, you use this exact toolkit all the time. Imagine you're a salesperson paid a base of $50 a week plus $3 per sale, and you want to make at least $100. Well, you can just set up an inequality. 50 plus 3x is greater than or equal to 100. And boom, you can immediately solve for exactly how many sales you need to hit your target.
Let's step into Section 4, Geometry and Scale Drawings.
So, the truly crucial point of this geometry curriculum isn't just memorizing a bunch of dry formulas. It's about practically applying them. It's about computing actual areas from scaled blueprints, or predicting the geometry of sliced three-dimensional objects. When you look at a scaled drawing of a house, you use proportional reasoning to figure out the actual square footage of the living room, right? Or imagine taking a three-dimensional rectangular pyramid and slicing it straight down the middle. Being able to describe the two-dimensional cross-section that pops out, that requires some incredible spatial reasoning. We also use known facts, like the fact that supplementary angles always add up to 180 degrees, to act as mathematical detectives, solving for unknown, hidden angles in complex structural figures.
And finally, Section 5, Probability and Random Sampling.
By analyzing a representative random sample, we can confidently draw inferences about a massive population. This works whether we're checking the average length of words in a huge science book or forecasting the results of an election. I mean, it is obviously impossible to ask every single person in a city how they plan to vote. But by using a truly random representative sample, we can generalize the data with surprising accuracy. We can even compare two entirely different populations. For instance, by comparing the mean heights and looking at the visual overlap on a dot plot between a basketball team and a soccer team, we can make mathematically sound comparative inferences about their varying distributions.
Now, there's this constant tension in statistics. It's perfect theory versus messy reality. On the left side of the equation, we have mathematical perfection. If we draw a name from a hat, we can calculate the exact uniform probability of drawing one specific person. But then, on the right, we have reality. If you spin a penny on a table or toss a paper cup in the air, you have to collect data on what actually occurs. Developing a probability model based on observing these real-world frequencies, well, that's exactly how we make sense of a completely chaotic universe.
For example, think about rolling a standard die. If you roll it 600 times, the perfect model predicts you're going to roll a 3 or a 6 roughly 200 times. Why? Well, there are 6 sides to a die. A 3 and a 6 represent 2 of those sides, which is 1/3 of the total outcomes. 1/3 of 600 rolls gives us a theoretical probability of exactly 200 occurrences. But if you actually sit down and roll that die 600 times, you might get 195 or maybe 208. Comparing that perfect theoretical model to the actual, messy, observed frequencies and trying to figure out the discrepancies between them is literally the heart of statistical analysis.
To wrap up this explainer, I want to leave you with one final provocative question that proves the math of comparison is literally everywhere you look. We've unpacked ratios, mastered the translation of percentages, mentally measured blueprints, and even calculated the odds of random chance events. This 7th grade toolkit isn't just something to pass a test and forget. It's a fundamental operating system for evaluating the world around you. So take a second, glance at the dimensions of your desk, check the battery percentage on your phone right now, or try estimating the unit price of your morning coffee. The mathematical relationships are just waiting to be uncovered. Thanks so much for exploring this with me, and keep questioning the quantities around you.